From the section on cylindrical coordinates, equation of motion, cylindrical coordinates from chapter 13, I'm going to do some problems. Let's start with problem F1314 on page 157. And it talks about a vertical curved tube with a ball to the inside. There's air blowing, and we know the shape of the tube is defined by this polar equation, 0.6 sine theta. And then we're through observation, we know that theta increases with time, like pi t squared, where t is time in seconds. And we want to find the magnitude of force F exerted by the air. The blower blows air, and yeah, so when t equals 0.5 seconds, okay? All right, so t equals 0.5 seconds, we have, we can calculate the angle. So theta is going to be pi times 0.5 squared. So 0.5 squared times pi. This is 45 degrees, or pi over 4, 45 degrees. Okay. And then we can calculate the radius r, corresponding to pi over 4, so it's 0.6 times sine of 45 degrees, 45 sine, that's square root of 2 over 2 times 0.6 equals, it's 0.4243 meters. Okay, so this is at the instant we are we want to find the force F. And the figure in the book is suggesting that theta is 45, and force F now is going to be tangent to the path. Okay, so upon the ball there will be three forces acting. There's the force caused by the air, there's weight, m times g, and then there's the reaction from the wall of the tube. Okay, now continuing to believe the figure, it looks like the force F is vertical. So, and vertical is the tangent to the path, and I have the reaction from the wall. Let's call it N now. And what else we know from the text equation? The equation 1310, that the angle made by the tangent with the radial direction, that is this one, I call it phi, it's given, so phi tangent of phi is r over dr over d theta. Okay, at that instant. So since we have to calculate dr over d theta, we can do it now, and will serve to evaluate the accelerations. So what is dr over d theta? Okay, so where shall I fit this? Maybe continue just the equation. So I have R, and this is for theta equals 45 degrees. So I have R at 45 is 0.4243, and the theta is going to be 0.6 times cosine theta at 45 degrees. Okay, so let's see what this is equal to. I still have 0.4243 on the calculator, and I say divided by 0.6 divided by 45 cosine equals, take the arctangent, and it's 45 degrees. So from here I have phi equals 45 degrees. Okay, so it's apparent that from this analysis, apparent that the okay, so we have the line of action of F along the tangent. This angle is at 45 degrees from R. So we are going to, let's look at some angles. I have 45 here, angle theta, and this is also this angle. Okay, whether it's 45 degrees is a particular angle because complement to 90 degrees is the same. Okay, but we do have, because they are mutually perpendicular, this one perpendicular to this and this perpendicular to this, I have this as theta. Okay, and there's 90 degrees between direction of UR, unit vector UR, and unit vector U theta, so this is also 45. Okay, so what do? We write equations of motion as sum of forces in the radial direction equals mass times radial acceleration in AR, and we sum forces in the theta direction. The increase of theta positive is going to be, as shown, UR is away from the polar point, so it's mass times acceleration in the theta direction. Okay, so what do we have here? For sum of forces in the R direction, we are having the projection of F, and it projects with sine of theta. So I have F sine of theta. Okay, and then I have projection of the weight, so it will be minus mg, and this is projected with also sine of theta. Okay, so if you look at the figure now, this is theta, and then so positive, negative. And then what else? We have also the reaction from the wall of the tubing. It's going to project in the radial direction as so let's see, what do we have there? The angle that is 45, or the theta, 45 would be either one. So if we look here, all right, so we have, this is theta, This is going to also be equal theta. Okay, so we have negative n times cosine theta. Okay, and this is equal to AR, which we're going to calculate separately. For the in the theta direction, we have the this f cosine theta. Okay, and I have negative mg cosine theta, and then I have n projects with sine theta, but in the positive direction. This is acceleration in direction of theta. Okay, so let's calculate the two acceleration. AR, it's the equations are repeated here in the text. So r double dot minus r theta dot squared. So it's r double dot minus r theta dot squared. Okay, and we need to evaluate the two at t equals 0.5 seconds. So what is r double dot? We have r dot is 0.6 times cosine theta times theta dot, and then r double dot is negative 0.6 sine theta times theta dot squared plus 0.6 cosine theta times theta double dot. As for theta dot, we have 2 pi t, and theta double dot is 2 pi, and this is a constant value. Okay, so let's go back here. We have let's because they occur above, let's calculate these two. So this is constant, and theta dot at t equals 0.5 seconds is going to be so 2 times 0.5, it's pi at t equals 0.5 seconds. Okay, so the r double dot now is going to be negative 0.6 times sine of 45 degrees times pi squared. So this is at theta is 45, t equals 0.5 seconds. Alright, so, and then plus 0.6 times cosine 45 degrees times 2 pi. Okay, let me pause. Alright, so I calculated r double dot at 45 degrees and t equal 0.5 seconds. And I've got negative 1.5216. It will be meters per second squared, has units. So you have it here, negative r at that instant. We have it calculated at here, so negative 0.4243 times, and we have theta dot calculated as pi for t equals 0.5 seconds. Okay, so I've got AR. For a theta, this is R times theta double dot plus 2 times r dot times theta dot, and what do we have? So we have r.4243 times 2 pi squared plus 2 times r dot is 0.6 times cosine at 45 degrees, and then times theta dot, that's pi. Okay, so let's see what that is. I'm pausing. All right, so I have the two accelerations calculated numerically for the given instant, and so this and this becomes known. What are the unknowns in the two equations? We have two unknowns. We have the F force, and the one that's explicitly required, and then we have the normal force N. So we have two equations with two unknowns, and we can further work or simplify this. You know, move this would be a known term, move it to this to the right, and let's see, and we can solve for n from one of the equation and substitute it in the other equation. All right, so let me pause again. All right, so the set of two equations is this one now, and why not take advantage of the fact that sine of 45 and cosine of 45, they're equal, so this is going to be square root of 2 over 2, 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 okay? So if we add the two equations, we're going to get plus and minus, this cancel out, so it'll be 2 times f times square root of 2 over 2, so it'll be square root of 2f on one side, and then again sine of 45 degrees is square root of 2 over 2, n equals to cosine of 45 degrees. Okay, so I said we add them, so from this value we subtract 4.3217, so negative 3217 equals, so this is 16.482, and force F is going to be 16.482 over square root of 2. So let's see, over 2 square root equals, so F is 11.65 newtons, and this is the answer.